Okay, welcome back. We're on our next application of Schrodinger's equation, and this one is commonly known as the particle in a box, or more formally, the infinite potential well. Now, unlike before with the free particle or electron in free space example, where the boundary conditions had a small effect because the particle was in a large box, we ended up constraining it to a large box. In order to do the normalization, it had to be in some non-infinite space. But here we're going to have a small box, a box that is small enough that the boundary conditions are going to have a major effect on the wave function. So now, as we've said before, the potential energy function is going to determine what psi looks like. So now our potential energy function, we're going to take it in this way. We can write it that inside the box, or inside the well, the potential energy is 0. And then outside the well, it's infinite. Thinking back to our boundary conditions, this is going to allow the derivative of the wave function to be discontinuous. But now, where is this well? Let's orient our well so that it's between x equals 0 and a. So that's where it is, the potential energy is going to be 0 in that region. And then outside that region, so for x less than 0 and x greater than a, the potential energy is infinite. And we can sketch this, sketch the potential energy function in this way. So here is our box is a units wide, and so a has a dimensions of length, and so here it is. There's a, and then we can sketch our function, our potential energy function, in this way. So it's 0 here inside the box, and then outside the box, it's like our well has walls, but they're infinitely high. Now, if we had a lot of time, we would do the particle in a finite well, and so the height here would be some finite number, and we could actually show that as that number goes towards infinity, then that solution would converge to what we're going to find directly here. But in any case, we have a potential well, so inside the well, the potential energy is 0, and then outside the well, the potential energy is infinite. And this is going to mean, thinking ahead, that the particle it cannot be in this region or this region. It's going to be confined to the middle region between 0 and a. In fact, let's just go ahead and label those regions. This is, by the way, figure 2.5 in our textbook. Over here for x less than 0, this is region 1. We'll call that region 1. Between 0 and a, inside the well, or inside the box, we'll call that region 2. And then over to the right, for x greater than a, we'll call that region 3. And we can write down Schrodinger's equation. I'm going to write it down in a slightly different form, just do a little bit of algebraic manipulation to get it into this form. Nothing new, nothing terribly surprising here. The second partial of psi with respect to x, and we multiply times negative h bar squared over 2m to get this form. Or by 2m over h bar squared. So we have second derivative of psi plus 2m over h bar squared times e minus v of x times psi of x equals 0. So this is a general form of the time-independent Schrodinger's equation in one dimension. We have not used any information here yet in it. Now, here's our strategy. Here is our strategy. We're going to set up Schrödinger's equation in each of the three regions, or at least in this case, we're going to have V be infinite in regions 1 and 3, so we're just really going to make a conclusion that Schrödinger's equation has to be satisfied in those regions. So we'll make a conclusion there. But if we, in general, we could solve Schrödinger's equation in the three regions, come up with a psi for each of the three regions, and then apply the boundary conditions at the boundaries, and then to tie the solutions for each region together. So there'll be a solution for psi in region 1, a solution for psi in region 2, and a solution for psi in region 3. The boundary conditions will tie these functions together by looking at them at the at x, in this case, x equals 0 and x equal a, because one of our boundary conditions is that psi has to be continuous. All right, so let's see what that does for us. Let's see how this works. Oh, and I guess, the final step, by the way, is normalization. So after we've gotten, we'll find the form of psi in each region, tie them together at the boundaries, and then we'll apply normalization. All right, so here we go. In regions 1 and 3, so this is our step 1, solving Schrödinger's equation in all three regions. Well, Schrödinger's equation in regions 1 and 2, 1 and 3, so v of x goes to infinity, and the way that we have to solve this, the only way that can work is for psi to be 0. So we're assuming then that the energy is finite, and it is. I mean, it could be large possibly, but it's never going to be infinite. So E is finite. This is going to imply that psi of x is 0 in regions 1 and 3. Now, so that we can call that kind of part A of step number 1. Part B of step number 1, in region 2, V is 0. And so Schrödinger's equation, we've actually seen this before with the free particle, psi squared, second derivative of psi with respect to x plus 2me over h bar squared times psi of x equals 0. This is exactly what we saw with a free particle. Now, we do have different boundary conditions in this case. And we saw last time with the free particle that we could express psi as a complex exponential. There'd be two, one forward traveling wave and one corresponding to a forward traveling wave and the other part to a negative traveling wave. In this case, it will be more convenient if we do express this in terms of sine and cosine. So we have two forms of the solution that we could work with. One would be complex exponentials. So we could say psi of x is a e to the I kx, sorry, I'm only using j, jkx plus b e to the negative jkx, where k, our wave number, is square root of 2me over h bar. Or, so this is what we had that was convenient for our free particle. But this form is going to be easier to work with for us now. Psi of x could be a different scale factor. We have a and b to be determined from boundary conditions. But here we have a different constant there. C times sine kx plus d cosine kx. Same k, the same wave number. So let's work with this one. Let's work with the second form. And then we'll apply our boundary conditions. Well, we can write down what we've got so far. 0 in region 1, so for x less than 0. C sine kx plus d cosine kx for 0 less than x less than a. And it's going to be 0 for x greater than a. However, I've said less than, strictly less than. The boundary condition that psi be continuous means that we can say that when x is less than or equal to 0, it's equal to this. When it's less than or equal to, or greater than or equal to 0, less than or equal to a. This all has to be true for psi to be continuous. So psi of x continuous, one of our boundary conditions, then if we look at x equals 0, that would mean that psi of 0 is equal to 0 from considering region 1. And then region 2, that's going to be c times sine of k times 0 plus d times cosine of k times 0. Well, k times 0 is 0. Cosine, let's go back here. Sine of 0 is 0. And the cosine of 0 is 1. So this gives us 0 is equal to d times 1. Oh, so d, this factor, is equal to 0. Okay, so we know something more, that in region 2, therefore, in region 2, psi of x is equal to c sine kx. And again, k is square root of 2me over h bar, like we've said, our wave number. All right, so we've made that progress. Now, let's apply the boundary condition that psi be continuous at x equal a. Continuous everywhere, but this is where we get some information. So at A, looking at region 3, where psi is 0, we get that it's 0. And then in region 2, we have c times sine kx, whoops, but now x is a, and that's equal to 0. So we have c sine ka equals 0. Well, c cannot be 0, otherwise our wave function is 0 everywhere, and our particle doesn't exist anywhere. So, we can divide through by c, because c is not 0. All right, this means that sine Ka is equal to 0. And then, what makes the sign 0? Well, it's when the argument is a multiple of pi, right? So this means that K times A is n times pi, where n is an integer. Now, if n is 0, then, well, okay, hang on. Then K, what this means is that K, our wave number, is equal to n pi over A. There's only discrete values of K, our wave number, that are allowed. Now, if n were 0, then K would be 0, and we'd always have 0 times x, and we'd once again have our wave function be 0. So n equals 0 is not allowed. So, and if we really only need positive values, so negative values are just going to turn things around. So n is equal to 1, 2, 3, and so forth. We think it's positive integers. All right, so what does this tell us? Let's just kind of summarize what we've got here. So we now know that in region 2, psi of x is equal to c sine kx, where k is equal to square root of 2me over h bar, and that is quantized as n pi over a, where n is 1, 2, 3, so they're positive integers. Well, what about C? C we determine from the normalization requirement, the boundary condition of normalization. So psi is 0 outside the box, so that's going to integrate to 0. And so our normalization requirement, normalization boundary condition, one is equal to the integral over all space of psi squared dv. In our case, this boils down to the integral from negative infinity to infinity of psi squared, but up from negative infinity to 0, it's 0. Okay, we write it down like this in our case, negative infinity to infinity of psi x squared dx, but it's 0 for less than 0, it's 0 for greater than a, so this works out to the integral from 0 to a of c squared, because this is now a real function, sine squared kx dx, and k is n pi over a. Well, we can look up in our calculus textbook how to integrate sine squared, and we plug in values for things, and we eventually find that c, we can take as real, positive real, is the square root of 2 over a. This will satisfy our normalization requirement. All right, let's summarize once more what we've got. We've really solved the entire situation. We're going to investigate some of these the ramifications of this. So now we know that psi of x is 0 for x less than 0, less than or equal to 0, and x greater than or equal to a. And so it's outside the box, outside the infinite potential well. Inside the well, we've got 2 over a square root sine kx. So this is for x inside the box. We've got k is equal to the square root of 2me over h bar. And that is equal to n pi over a. And of course, n is equal to 1, 2, 3 positive integers. Now, this relationship right here is going to tell us energy levels. They will be discrete, quantized energy levels. And so E, we can call E sub n. It will be E sub 1 for the first energy level, and the second E sub 2 for the second energy level. So solving this equation for E, we find that E equal to E sub n is equal to h bar squared, n squared, pi squared, this is the normal form here, over 2ma squared. We have quantized energy levels. This also means that psi, there's only certain functions that work because n is quantized. So there's a psi for the first energy level, psi 2, psi 3, and their corresponding E sub n. And if you look in chapter 2 at figure 2.7, it shows you the n equal, what psi looks like for n equal 1, n equal 2. You can see that energy goes up as the square of n. And this sinusoid starts out with one bump, and then a whole period for n equal 2. For n equal 1, we've just got one hump. For n equal 2, we've got two humps. We've got a whole period. For n equal 3, we've got 1.5 periods of the sinusoid, going to 0 at x equals 0 and at x equal a. This is a result of our infinite potential well particle in the box. Interestingly enough, we can actually build these things with compound semiconductors. It was actually, and quantum dots are another way of creating actually this kind of a structure in the real world. And so you get discrete energy levels. This is why we get quantum mechanics. The particle always ends up being constrained, and that results in quantization in energy and everything else from that. All right, well, that's enough for today. Good luck.